Hi, my name is Josh. I'm from Columbia University. So in this paper, we're studying the computational complexity of attention. So attention is this problem that you have to solve over and over again when you're doing training and inference in large language models. And the most straightforward algorithm for it runs in n squared time, where n is the sequence length that you're modeling. And we ask in this paper, is it possible to do faster than that? So this is actually the second in a sequence of 2 papers. So let me first tell you a little bit about what we proved last time. We proved that there's a strong dichotomy about whether or not it's possible to do faster, depending on one particular parameter that we call b, which is an upper bound on the magnitudes of the weights of your model. So if the weights are all small, less than some particular threshold that ends up being square root of log n, then we actually give an almost linear time algorithm to solve the attention problem, so you can compute it as fast as you could hope for. And by contrast, if b is bigger than that same threshold of square root of log n, we prove a corresponding lower bound that shows not only does our algorithm not work anymore, but more generally, it's just not possible to solve attention in subquadratic time, assuming this conjecture called the strong exponential time hypothesis from complexity theory. So when b is small, our algorithm runs as quickly as you could hope for, and when b is big, not only does our algorithm not work, but it's just not possible to solve the problem in subquadratic time. Then in this paper, we studied the backward computation problem. So, when you're training your language model, you have to do alternating forward and backward computations. And the backward computation of computing the loss gradient of attention a priori seems like a more difficult problem. I actually thought at first we'd end up proving that it's harder than attention somehow. But our main result is actually the exact same thing for the backward problem, that it can be solved quickly for this exact same threshold on the weights of the model, and cannot be solved quickly for this exact same threshold. So now both steps of training can be solved quickly if and only if your weights are small.